Dr. Jianping Pan, Professor of Computer Science at the University of Victoria.
Yeah, I was a student 30 years ago.
Okay.
I want to use my computer so I can show you some video demo as well. Hopefully this can show up. Okay. Yeah, great. So again, my name is Jianping Pan. I'm from the University of Victoria in BC, Canada. And this is a project with my colleagues cross-country from University of Victoria, Manitoba, Waterloo, and University Newfoundland as well. It's sponsored by the NSERC, just as NSF in Canada. It was inspired by another Dave who come up with the idea about the testbed. So I think for this particular audience, everyone knows about the LEO satellite network, and there's 4 major players out there with different number of satellites running, and some of them are already in service as well. But what I want to see is LEO is more than just, let's say, broadband internet access. We have, let's say, a direct satellite to cell phone, and we also have Internet of Things in the space as well. And this Thursday, we have another panel about the data center in space as well, which I'm part of that. So I just mentioned those 4 leading players, and particularly we're focusing on Starlink because that's the biggest elephant in the room right now. And it claims it has 10 million users by the beginning of the year. And by developing a special technique from the internet, we can measure these 10 million users, and we can successfully reach, let's say, 6 million of them. So this is one of the purpose we see this is the largest test bed because we can cover 60%, even more than that, of the 10 million users out there. So you can see from this figure, we show the majority of Starlink users are coming from US and Canada, and also in South America as well. So in this case, we know, let's say, where the users are distributed, because Starlink only tells us how many users in total, but we also know, which country has how many users in that sense. So because it's a port-to-port covered, we also want to measure them around the world as well. So this is done by this winter. It's winter in the northern hemisphere, so it's summer down in the Antarctica. So we have many scientists working there in the research stations. Some of them brought the Starlink dish with them, and they have much better connectivity than whatever they have before. So we can see for these Starlink dishes, they actually clustered in the research stations, which is quite reasonable because you stay most of the time in the research stations. So this is the behavior for one particular Starlink dish. So here is the wall clock, the real time. And the y-axis here is the latency. So basically what we measure is the time between the port of presence for that particular dish to the dish itself. You can see very interestingly, the minimal latency changes over time in a periodic way. So this because for the low Earth orbit satellite, we can see them about maybe a few minutes. That's what our initial thought as well. So maybe after a few minutes, you have to switch to another satellite. But once we have done some measurement, we found actually Starlink does hand over much sooner than that. And every 15 seconds, Starlink switch to another satellite because you have more than, let's say, 10,000 satellites in the space, but you do have 10 million users on the ground. So that's why we have to shuffle these satellites between users to make sure everyone has a fair share of the satellite capability as well. So that's first discovery we found, okay, this is quite different from what our thought in terms of visibility. Next, we also put all these 14, let's say, Starlink dishes we discovered in the Antarctica in the same graph. And again, this is the wall clock, and this is their latency. So here you can see not only they switch satellite every 15 seconds, they also switch satellite at the same time or synchronized way. At least in the Antarctica, later we're going to see actually around the world as well. So you can see these delay spikes is the moment when the satellite switch between those for these dishes. You can see all these 14 dishes, they actually synchronize the switch over behavior as well. And this corner here is the Starlink behavior, let's say, in the Arctic Circle. Because up there, we only see a small portion of the satellites in going to the polar orbits. So this a black line, the white line here, is the trajectory of the satellite. So basically enough, we can not only know the dish is in the Arctic Circle, but we also know which satellite you're talking to as well. Same thing like for the dishes like near the equator here. And you also see a black band here. That's because for both the LEO satellite system and the traditional GEO, they use the same frequency bands. And the GEO has priority. So that's why kind of when the satellite go over the equator, above the equator there, they have to shut down for a while, because otherwise they're going to interfere with the GEO system. So that's why kind of the user always complain that why there's like a black band in my kind of field of view as well. That's because that's GEO satellite sitting there. So this is the test bed we're building right now. It's called like a CCC LEO, stands for the Coast to Coast Coast, let's say, kind of LEO satellite test bed. It covers all 10 Canadian provinces and the territories as well. So you can see like they're located like in each province and territory. And then now we're also expanding them into the US and other countries around the world as well. So there's some dish for this one is the dish like in Victoria. We put them in the whole building. And we also have some like hosts in different parts of the world, like this one in Ottawa and this one in Denver. Basically, they host our dishes. And we also put a small mini PC behind it to do all the measurement, automatic measurement like tasks. And from these dishes, you can see they see different part of the sky, because, for example, this part is obstructed by the roof. Someone just put a dish on their backyard, and the wave radio kind of like penetrated the roof, so you see the like red dots here. And we also see like the trees and things like that as well. So this test bed has starting, let's say, operating from 2023. And by now, we have collected more than 1 terabyte of the compressed trace data. And this has been downloaded around the world for 6,000 times. So that's a lot of data like accumulated. And next, I'm going to show you some of the work based on the data we collect by ourselves and also some by other people as well. All our work, paper, data, and the tools can be found at this particular portal link with the link to the testbed itself as well. For example, like when we collect enough data from the Starlink users, we can also map the Starlink backbone around the world. Starlink is quite unique in the sense like it's not only provide access network, but also provide, let's say, a backbone network around the world as well. So this is the Starlink backbone in, let's say, around the world. And this part is just I showed you about the handover behaviors. So initially we saw like you could hand over every, let's say, few minutes when the satellites are visible, but the Starlink indeed actually decided to hand over every 15 seconds. Later, I'm going to show like what's the implication of this like fast handover. And here is the Starlink like satellite you're talking to right now. For example, like our dish is in Victoria, so here is Victoria on the Vancouver Island, and the dish is here. And here we can see like at a certain moment of time, we're talking to a particular satellite. And after 15 seconds, like we switch to another one so that our delay goes up and our signal-to-noise ratio could drop down. So in this case, like you may switch to an older generation satellite. So that's why kind of the signal-to-noise ratio is lower in this case. So for comparison, I mentioned like there's 4 major players right now. In addition to Starlink, we also have some thing called OneWeb, which they have about 600 satellites running there in polar orbits. So their handover behavior is quite different because for OneWeb, the beam is fixed right now. So that's why when they go over the Earth's surface, they just scan through Earth's surface. So that's why you can see that their beam behavior is much more regular than the Starlink. But because they're a little bit higher in, let's say, kind of elevation, and there's a few, let's say, satellites out there with limited ground infrastructure, the latency is slightly higher than Starlink, but reliable, like more stable as well. So once we have the big picture about these like LEO satellite networks out there, we're going to dive into, let's say, some of them for, let's say, deep understanding as well. One thing we did is like, for example, like if this is your Starlink dish, and we want to figure out which satellite you're talking to right now. Before Starlink provides such information, it's in gRPC interface, but for whatever reason later they removed it. So for us, what we can do is like if you know like you're talking to a satellite in this direction, and then you can also link to the latency you're experiencing right now. For example, like this satellite is moving in this direction, and this is your dish. It actually moves closer to you. So that's why you see the minimum latency here goes down a little bit as well. That's because the propagation delay goes down. And after 15 seconds, Starlink switch you to another satellite. So this one is like the green one here. And after another 15 seconds, it's moved to even closer satellite, the red one. And then they realized they made a mistake because this particular satellite actually is moving away from you. So in this case, like it's not going to stay with you for a long time. So that's why the Starlink moves you back to this particular satellite, which is the same as the previous one here. So now we know like this particular handover is useless. Actually, you waste like enough handover opportunities, and you introduce like latency changes as well. So that's how we communicated this back to like Starlink. So now they remove this kind of like unnecessary handover in this case. So this is the work done by my student Ali, and he has now graduated like with the master's degree. So once we know the location of the satellite we're talking to, and also use the TRE data, which is public from because we have to, let's say, kind of track all the objects running in the space. So in this case, like enough, we know we're talking to satellite in this direction because we know our GPS location. We also know the kind of orientation of the dish. That's why kind of we know these are the satellites we're talking to, and we can map the location of the satellite to the identity of the satellite as well. So in this case, like we know not only the satellite right now, but also 2 minutes or even 2 hours after right now. So because the handover behavior, we found like enough, this actually introduced new challenges to the network protocols and applications as well. So one thing is like enough for the protocol we are running, we assume like enough the latency will be stable. But if the latency jumps up, you have like timeout. If the latency jumps down, you have like packet reordering, which all cause like a TCP throughput going down. So that's why kind of we found that these handover behaviors, they actually can align with the loss events in the TCP protocol as well. Not only in Victoria in BC, but also in Victoria in Seychelles, which is another place in the Mid-Ocean. So once we've identified the root cause of the problem, the fix actually is quite simple, because we just need to know, like, we're going to have a regular handover right now. We're going to freeze our congestion control algorithm for a little bit of while, about 100 milliseconds. So in this case, we can improve the throughput, and we can also reduce the transfer time, which is like improve the network protocol application and performance as well. So by applying the same idea, we can use this for the video streaming over, let's say, kind of Starlink or like a LEO satellite network. So this is a test bed our students did in our lab. We basically built a small Netflix in our lab with the kind of virtual machine in Seattle. We had the Starlink POP-ES, and we do video streaming. And by using the same technique, we can improve the like quality and also reduce latency as well. So these are some of the work we do, but we also collaborate with other people using like the infrastructure and also collect more data as well. So one example is like we put those Starlink dishes on vehicles, because so far you've seen like these dishes, which is stationary. So on Vancouver Island, we have some indigenous kids. They have to spend like a 2.5 hours every day in the morning and a 2.5 hour day in the evening going to another part of the island for school. So in this case, like the bus going through some like kind of winding, let's say, kind of highway, which is like no cellular coverage. So the parents and the teachers get worried about the weather and other things as well. So what we do is like we put a Starlink dish on the school bus. We also put a camera there because we want to like capture the obstruction on the dish by using a video camera to compare the like enough estimation about the obstruction versus what the visual, let's say, kind of ground truth is. And we also collaborate with people like from University of Minnesota to do, let's say, kind of this mobile Starlink dish on vehicles in the city, and also collaborate with people with the Northern East University to, let's say, kind of have a cross-country test among the kind of dishes along the way, because with different terrains and a different user population and a different like, kind of performance as well. Not only on the ground, we got into the airspace as well. So this is like one of the things that we do, like we basically build a small test bed node, which is about the size of this much, with the battery, with the mini PC, and all the communication necessary there. What you need to just like plug in the power plug, and then it does the automatic measurement by itself. So basically, for example, like in this case, we see like kind of the aircraft used to have, let's say, kind of a very bad internet because they are using the geo satellite systems. Now some of them have moved to LEO, Starlink or OneWeb. You can see like the throughput jumps up a lot, but more importantly, the latency, let's say, goes down dramatically because low latency there. So there's some experimentation we do, like how to do, let's say, video streaming or video conferencing on aircraft, although, of course, sometimes it's not allowed by the current regulation as well. I was like booked for a flight between, let's say, Seattle to Doha, like at the beginning of March, to a 6-hour, let's say, round trip to test the kind of Starlink performance on Qatar areas. But unfortunately, the trip got canceled due to the things happening in the Middle East. But that's why we also developed new techniques to measure the kind of Starlink performance on aircraft from the internet. So in this case, we don't have to take the trip, but we can measure the performance from outside in as well. So this is something like kind of we're doing right now. And if time allows later, I can show a quick demo as well. So far, all the things I have shown you to you is by the regular consumer level, let's say user dish. In addition to the user dish, Starlink also has something called a community gateway. They are about to change the name as well. So in this case, like enough, we have a small ground station look like infrastructure for a small community, most likely will be like island nation in the Pacific. So that's why kind of they use different frequency bands. That's why kind of they can reach like 10 gigabit per second, let's say, by symmetric link as well. So we can compare the performance with user dish versus like community gateway because we have like more bandwidth and also less competition because you can like have a very few ground stations or community gateways versus like thousands of, let's say, kind of user dishes. Just like in this room, if we double the Wi-Fi devices, the performance is not going to just half, but even lower because of the competition as well. So in this case, like you can see the community gateway now has much more better performance. These kind of gateway are not only like for those island nations, they're also moving on some of the biggest cruise ships, like the Icon, the Utopia, and the Star of the Seas. And the Star of the Seas is the first one to confirm it has the kind of community gateway, in addition to the like a regular, let's say, high-performance dish as well. Of course, like not only for cruise ships, but also for many like kind of shipping vessels across the different oceans there. So basically, kind of, we can think about like, these dots here are the vessels with the Starlink dishes. They cross the ocean as well. In this case, like they traverse different pops of the Starlink ground infrastructure because I mentioned like for Starlink, it's not only like kind of a satellite in space, but also like kind of ground infrastructures. And when you are like kind of in, let's say, Boston, your Starlink dish will be associated with the kind of pop in, let's say, New York City. But your ground station could be like either nearby or could be very far away. But nevertheless, let's say kind of your pop will be like gonna stay in like New York City. We're not only just like doing the things like on the ground and into the air, we're also trying to like reach the space with a CubeSat to be launched by the end of next year. So this is like a new contract from DRDC, the Defense Research and Development Canada, which is like the DARPA in the US, to develop a test satellite to be launched. And this test satellite is going to collect data from the space, from the air, from the ground. Meanwhile, it's going to use the laser communication links. Just as this morning mentioned, like it's pretty hard to point out to like laser links in the space because they're moving things around. With the commercial, let's say, kind of LEO constellation there, and then we can downlink the data to the ground to our like kind of Center for Aerospace Research at the University of Victoria. But we also have like radio links from the test satellite to do, let's say, kind of simple TTC things as well. So this is my last slide, and also my contact information as well. So one thing I want to bring attention to is like kind of we have all the information here at this location with the data set, with the kind of test bed as well. And you're welcome to use the data set, but meanwhile, kind of if you can, you're encouraged to maybe host a virtual machine or maybe bring something like this to your next trip, like on a plane or maybe like kind of on cruise ship as well. And next year, I probably can talk about like more about our test satellite to be launched by the end of next year. And it'll be in space for at least like 6 months to do all the experimentation as well. So that's what I have. And this Friday, I will give a guest lecture in like 1689, which I can give more details about all the things we have been doing.